All right. So Monday, I'm here. Means I didn't win the Powerball.
You didn't go to that fortune teller, huh?
No, I didn't. So I have to pick up another one. Long shot ticket. We can dream about winning it.
So as the Powerball gets more money in it, do more people play it?
Yep.
Does that thus increase the likelihood of somebody winning it?
Yep. Well, yeah, the individual has a fixed probability of actually winning it, but the chance that the chance that the drawing is going to have a winner is dependent on how many people buy it, how many people pay to buy the numbers. Yep. And that's also why it generally goes up slowly, and then once it hits, I want to say maybe about 400 million or so. When it gets to like 350 to 400 million, the jackpot, then you start seeing it jump up much more quickly because there's more and more people buying into it. I don't do like the double. You know, they ask you, oh, do you want to buy at the double of? I don't know. There's some option that'll double your winnings if you hit it, with the exception of if you hit the jackpot. Going for the jackpot, I know they want nines. Why would I pay an extra $2 or an extra $1 or something?
It goes towards help funding schools, right?
It goes towards help funding schools.
That's why you pay the extra $1.
I've got, yes, and you know what? I have some fantastic beachfront property in Arizona for you too. I know. Don't get me started on that. I know it's supposed to go, and it does. It does. They have the fund for it. That helps, but
Not all of it.
yeah, not all of it. And then they tax you. Not only are they taking a cut out of it, but then they also tax you on the wins. Like, that's double taxation. But whatever.
That's why my mom was like, if I ever win, my mom's an accountant. She's like, this is how you go about not getting your winnings taxed away.
Yeah.
And I was like, okay. If I ever win the lotto, I will call you. If I ever win the lotto, there will be a lot of things to be doing.
Oh yeah, so yeah, if I hit the lotto, I'll probably still be here. We might have a short class day there. All right, so let us do these problems. So we do have lab today. Again, we're gonna continue our discussion with the normal distribution. I didn't look. Our exam, I think, is in 2 weeks. I think we've got this week and next week, and then our next exam. So it turns around pretty quickly, but our exam covers the probability. It covers this normal probability. It covers assessing normality, which is what we'll cover. So here's these practice problems. All right. What we're going to do is I'm going to work through them, how I do them on the board. All right. And for those that are watching, I have my table here. All right. So this is my normal table. We're going to use this to find our actual numbers. So I'm going to work this up on the board, and then we'll kind of double check our answers. I'll have to come up and actually, I think I might have a printout of it. Let's see if I've got a printout. But I'm going to work this through as if I was working through the problem, and hopefully we can kind of make it a little bit easier to see what all we're doing here. I got my T-table. Oh no, I don't have the normal table. That's okay, because I have 800 print credits, so I'm going to go ahead and print it, if it works. If it works.
That's what you said. I'm going to go ahead and print it. I was like, very confident.
Oh, something's printing, but that started before I hit print button. Somebody else must have printed this.
Oh, yeah, I
Front and back?
You know what? It's my son of a gun.
How'd you get front and back? I didn't get front and back.
Did he select?
It's still waiting. I thought I printed both sheets of paper. It printed one.
Was it trying to print front and back and you just messed it up?
No, I didn't select the option. I didn't know I had the option front and back. That works.
Do you want this one?
No, that's okay. All right. So, let's do this. We're going to zoom this in, and we are going to relocate to the front board. Got this up here. And this might be extra for some of you that feel pretty confident working through it. For others, so hopefully clear things up. This is actually how I'm going to do it by hand. Is the same general process that I'll use if I'm working in R. So our next slide has how to do this stuff in R. So we'll check all of our answers using R. So first question. Make sure get my left and right set. Oh yeah, okay. All right, so our first question has population of words with an average length of 28 millimeters. What's the probability that you find a word that's larger than 33? So we're going to start just drawing it out. All right, so our population of worms looks something like this. So we have, this follows a normal distribution with a mean of 28, standard deviation of 3.5. All right, so that's our normal curve. So we are centered at 21. All right, we're asking, what's the probability that we find a worm that's larger than 33? So there's our 33, or approximately. There's our 33. So we are looking for the probability of finding a worm larger than this. So since we're dealing with a continuous distribution, we're looking for that area. All right, that area under the curve. So of our sheets, I'm using the sheet that has that tail as our area. All right. So our question, what's the probability that we get a worm X that is greater than 33? And I'll tell you now that it can be greater than or equal to, we still get the same, because the actual probability of getting a 33 is so small that we get the same answer if it's X is greater than 33 or X is greater than or equal. All right, so we have that. We want to use our tables. So in order to use our table, we need to get to the Z. So recall, our Z is equal to X minus a mu over our sigma. All right, so what is that? Well, our X value is 33. That's what we're looking for, all right? And what we need to do is get this to a Z, because that approximates a normal curve with a mean of 0 and a standard deviation of 1. So what we do is basically take all of the values here in our distribution, subtract 28. When we subtract 28, we're going to cause this curve to shift all the way over till it's centered at 0. And then what we're going to do, we still have the standard deviation 3.5. We're going to divide by 3.5. Take 3.5 and divide it by itself. We take this curve, we're centered at 0. Now we're going to shrink it, or compress it, so that we get a standard deviation of 1. But if we're going to do that with the entire distribution, like 28, we also have to do it with this number. So I'm going to do this X minus our mean, which is 28, divided by 3.5. And if I do it to one side, I have to do it to the other side. All right, so now that converts our X down to a Z. So this here changes it to Z. And then this 33 minus 28 over 3.5 is, pull out my calculator. One point 428571429, probably a sequence of numbers. But I'm going to go to 2 decimal places because that is what's on our table, 2 decimal places. So now I have my z. We're at a normal 0, 1. That's what our table is working on. We're looking at that probability greater than 1.43. So I'm going to go down 1.4. All right, so I've got my row with a 1.4. Now I read across until I get to the 0.03 column, and I get 0.0764. So that's our first answer. All right. Question on number 1. Number 2, average scores of NFL games. So the average score in 2017 was 21.7. You can look it up. Standard deviation is 10.2. Again, you can look it up. So what's the probability that a team scored less than 9 points? So I'm going to draw this again. So our average is 21.7 with 10.2 standard deviation. So it doesn't have to be exact, but we know that we are centered at 21.7, and then our sigma is 10.2. And we are asking, what's the probability that we'll score less than 9 points? We are way over here. Well, not really. If we think about where we're at, standard deviation is 10. We're about 1 standard deviation place. Maybe about. So there's our 9. We are looking at this area. Alright? So we're going to start with x is less than 9. That's what we're looking at. We know that we're normally distributed. So we're going to convert this to a z. We do that by subtracting the mean and dividing by the standard deviation. 9 minus 21.7 over 10.2 gives us a z that's less than z is less than 9 minus 21.7 divided by negative 1.25. Negative 1.25. All right. I'm going to mark this down. This is from here to here. It's 12.7. 12.7. 1.25 standard deviation. We don't have a negative 1.25 on our table. Our table is always to the right or to the left of a point. So in this case, we're on this side. We don't have a value for a table to give us that number. But you should recognize that we are symmetric around the mean. So if we are 12.7 units away from our mean, if we go 12.7 units above, which is 34.4, then this area is going to be the same as this area. Not only that, but when we apply this transformation, get our z, this part is the probability that z is greater than 1.25. So since we are a mirror image, we are symmetric around the mean, this slice is the same area as this slice, which is this z is less than negative 1.5 is the same has a probability that z is greater than 1.25. So again, if we multiply by -1, we ignore it on our z. Negative z is greater. So negative z is greater than 1.25. But when you multiply by -1, you flip our inequality. So those are the same probabilities. This probability is on the table. Right? So if I go to 1.25, 1.2, so I go to 1.2, read across the 5, I get 0.1056. Not too bad. Right. This. Number 3, average length of the mobile phone call is 1.78. That is, when I look these up, yep.
I do have a question about number 2.
Okay.
In NFL, can you score half points?
No, but the average goes to one more digit than what was measured. So all of the scores are whole numbers, but when you calculate the average of the whole numbers, your rounding goes to one more digit.
Which is what makes it continuous versus discrete, right?
What's that?
Which is what makes it continuous versus discrete, right?
Yeah, so the numbers are discrete. Yeah, the numbers are discrete, but the average reflects more of a continuous. Oh, good. On the same question. Average. All right, so average length of mobile phone call is 1.78. I did standard deviation 0.6, but then I had to make that number up. They didn't report those. So what's the probability that a phone call will last between 1 and 2 minutes? So we're just kind of building on it. So here's our curve. All right, we are centered at 1.78. 1.78. Our sigma is 0.6. Now we ask the probability that a phone call lasts between 1 and 2 minutes. So we've got 1 down here. We've got 2 up there. So we are looking for this slice underneath that curve. We're looking for that area. All right? We're looking for that area. So how do we do it? Well, what we can do is break it up. So 1.78, there's our 2. We can go ahead and calculate this entire area. So the probability that x is less than 2. We can do that area because we've got a table that covers that entire area. But then we don't need that slice, right? So if we do probability that x is less than 2, it gives us that entire area. We don't want that area. So then what we can do is subtract that area that is less than that 1. Would that give us the area of interest? Yep. We can start with the big part and then we subtract out the other part that we do not need. So on here, we're going to be doing it the exact same way. We have to subtract our mean divided by our standard deviation. And we have to do it on both sides, both inequalities. Ahead. So now we have our z is less than 2 minus 1.72 over 6. 37. probability that we are less than 0.37 standard deviations away minus z is less than 1 minus 0.78 should be a negative. Negative 1. Alright. So we've got the same type of situation. This one we can use on our tables. So that's on the first page of that table. We're to the left of the line and we are above that 0. So 0.37, 0.3, read across the 7, I get 0.6443. That's what that is. We're going to subtract this part. But again, this part, z is less than negative 1.3, is the same as z being greater than positive 1.3. So then we go to that second side. 1.3, I get 0.0968. So our answer is 0.6443 minus 0.0968. 0.547. The almost 55% chance that we're going to have a call between those two. So take the whole, subtract out the slice that we don't need that part. That's what that's all right. And last one, 0.0764. 2 is 0.1056. 3 is 0.547. All right. Got these down here. Our last one. The average height of men in the U.S. is 70 inches. What's the probability of meeting an American man between 65 and 68 inches tall? That's a little bit of a trick question. We have to figure out first what's the probability that we encounter an American man. Right? Kind of a complex problem. But so we're going to avoid that. We're going to assume that anyone that we meet is technically American, so we can use our curve. So we are centered at 70. Standard deviation is 3. We are asking what's the probability of meeting an American man between 65 and 68. So there's 68. There's 65. We are looking for this slice. That's our slice that we're looking for. So we can do basically the same thing. We're going to do probability that x is less than 65. So we're going to do the big chunk first. And then we're going to subtract out 60. We're going to do 60. We're going to do 68 chunks first, the big one, and then we're going to subtract out the tail, which we do not need. So, probability of x is x minus 70 over 3, 68 minus 70 over 3, minus probability of x minus 68 divided by 3, 65 minus 68 divided by 3.
Why are you using 68?
Sorry, 70. I don't know why I did 60. Just throwing me off. Minus 7. Minus. So So we've got this probability that Z is less than negative 2/3. Now do 0.67 minus probability that Z is less than a negative 5/3. Negative 1.67. All right, but we're in the negatives. We don't have a table that allows us to do this, so I'm just going to flip it for the mirror images. So this is Z is greater than 0.67 minus the probability that Z is greater than 1.6. Now we use our table. That is a table with the tails. So 0.67, I get 0.2514. And the 1.67 is 0.0475, which gives us a total of about 0.2039. 203. Get it? There's our summary. Our answers. All right. There we go. All right. Now, calculating probabilities in R is actually fairly easy. For these, we're going to use P norm. And actually, P in the distribution name will always calculate our probabilities. All right. The nice thing about R is that we don't need to do the Z. R will do it for us. All right. Because what we can do is give it the population mean and the population standard deviation, and then R will do it. R will calculate it. The only thing that's different for us is that we have to specify the lower dot tail. All right. So what lower dot tail is asking is, do we want the area to the left of our value, or do we want the area to the right of that value? If we want it to the left of our value, we'll say lower dot tail equals T. If we want it to the right of our value, then we see it say lower dot tail equals F. All right, so example 1 was our wing length of roaches. We did that Friday, maybe? All right, and we did it by hand. But at that time, I didn't really go through how to, like what I did up here. I didn't draw the curve or anything, all right? Because we didn't really need to, all right? Because we were focused on just calculating that Z value and then using the table to get it. So here's how we would do it in R. All right, wing lengths of roaches is approximately normal, mean of 15, standard deviation of 2. And we asked, what's the probability that we would find a roach with a wing length less than 18? All right, so actually, let's do this. Normal probabilities. All right, so let's get this example, roach example. So wing lengths are normal. Normal 15 comma 2. What's P? X is less than 18. This translates to what? That's quotation. What's the probability of finding a roach with a wing length less than 15? Should probably do this. There we go. All right, that's what it's doing. All right, I'm gonna have a chunk here. But before we do that, I'm gonna kind of lay out the function that we're using. All right, and then we'll describe the function for the roach example. So we can calculate normal probabilities, aka area under the normal curve, using the function p norm x mu sigma lower dot tail. All right. X is our value, which is given in the problem. All right. Mu and sigma, these are the mean and standard deviation of the population. I'm going to say the X is our value, which is given in the problem. Yeah, we'll just leave that there. All right. Lower dot tail. This option takes T or F, which translates, I guess not translate, I don't want to do that, which means T or F. So T, and we'll give an example of this. T, which is area to the left of X, or F, which is area to the right of X. All right? So for example, let's move this up, get this up a little bit higher. So for example, if we do probability that X is less than 165, then we use lower dot tail equals T. P, where X is greater than 165, then we use lower dot tail equals F. So basically it's saying what part of the tail are we calculating the cumulative probability of? Is it going to be to the left of our value, or is it to the right of our value? All right? And you can see it when we draw it on a curve. Like if we draw a histogram and say, okay, what area are we looking for? That tells us, are we to the left of that or to the right of that? And that helps us identify if it's lower dot tail equals T or lower dot tail equals F. All right? So for us, this roach example, the wing lengths are normally distributed with a mean of 15, standard deviation of 2. We ask, what's the probability that we find a roach that's less than 18? All right, so do we have to draw anything out? Probably not, but it could help. I say probably not because we already know, based on the problem, if we need lower dot tail equals T or lower dot tail equals F. So which one do we need? T, right? So we have a 15-2 curve. Here's our 15. We're asking for 18. It's once less than that. So we are doing a lower tail because it's lower than the 18. So this is lower dot tail equals T. All right? Lower dot tail equals T. I guess I better email. holding it freehand. See it? So we got lower dot tail equals t. That's what we're trying to find. And then we will use r using the p-norm function and just type it out and substitute everything that we know. So we're asking if p is less than 18. Well, it's p-norm. 18, that's our value. That's what's given in the problem. And then our mean is 15. And our standard deviation is 2. And I like actually writing out what the mean is and what that standard deviation is. So mean equals 15, ST equals 2, just for me to keep track. It's easy for me to see, did I mess something up? Now, the default is lower dot tail equals t. That's our default. But again, I like to spell it out so that I know that this is lower dot tail equals t. I'm to the left of our point. All right. So based on the question, we want to use lower dot tail equals t. So when I run this, I get 0.9331928. Is that what we obtained in that Roach problem? Yep, we did. P-norm, 18.5. Actually, let's go back. Right there. This is our problem. This is how we did it. And then we calculated probability, which was 1.9332. Right on our first column. All right. So matched. Did we have to calculate the z? Nope. R did it for us. R will do it for us. So using R makes it a whole lot easier, right? All right. So additional practice problems. These are the same practice problems that we did up on the board we just did. So go ahead and use R, use the p-norm functions, all right, and get this. Now remember, how I had split it up on the board, I made it so that when we had slices, instead of like a complete area under the curve to the left or to the right, when I did slices, I subtracted out a portion. You're going to do the same thing, but remember, you're not doing subtraction in the p-norm function itself. You're first calculating areas and then subtracting out some areas. So what I'm going to do is give you some time to go through this. It's 11:38. So it shouldn't really take you all this time to do it, but I think what we'll do is work on this now. I'll kind of walk around, help you out, get your values, make sure you match, and then we'll pick this up in lab. Because I think it'll take 5 minutes maybe to do it, and then in lab we'll talk about deviations from normality and how to assess normality and so forth. All right? We do have some homework that's supposed to be uploaded today. So if you have questions on that homework, go ahead and bring it to lab and we'll look at it. All right? Get this set. So those of you at home, work on it, and then we'll see you at 2.